My name is Jacek Kunicki. I work at Software Mill. We are a software house that is 100% remote and 100% flat. So if after this talk you would like to talk either about Akka streams or about remote work or about flat companies, feel free to catch me tonight or tomorrow, whatever you wish. So Akka streams is one of the implementations of reactive streams. Reactive processing is a very hot topic today. So let's just do a quick recap of what stream processing is actually about. So in the general architecture, you basically have some source of your data that's called the producer. Then you have a consumer, which is like the ultimate place for your data. And you have a number of processing stages in the middle that do something with your data. And normally you have data flowing from the producer through the processing stages to the consumer. So this is like a general architecture, and you may ask yourselves what is different about reactive streams. So in such a pipeline, you can imagine two scenarios. The first scenario is where we have quite a slow producer and a quick consumer. And then, well, it's actually no problem, because when the producer is slow and the consumer is fast, the consumer can work very quickly, and well, the producer can produce some data, but in a slow manner, so the consumer never gets flooded with data. But in the opposite scenario, where you have a very fast producer and a slow consumer, there is a risk that, well, the consumer is going to receive too much data, much more than it's actually able to process. And in this case, well, there are different strategies that can be used. For example, well, the consumer can break. It can try to reject data, which is actually happening in network hardware, for example. The routers are just dropping packets when they can't handle them. But in reactive streams and the idea of the reactive manifesto, we have something that is called back pressure. And back pressure is basically a way for a slow consumer to signal demand to the producer. So in a back pressure scenario, the consumer tells the producer, hey, I can accept n items of data, like in this slide here. And then the producer knows that he cannot send any more than like a certain amount of data, because if it did, the consumer wouldn't be able to consume it. So this is the general architecture of a stream processing pipeline with the general terms. Now, in Akka streams, the concept is similar, but the names are different. So the producer in Akka streams is called a source. The consumer is called a sink. And the processing stages in the middle are called flows. And all the things together form a graph. And actually, in terms of the API, both source, sink, and also the flows are graphs, which have a given shape. But those are like API-specific things. You will see them in the code later. So we have graph in two places. Graph in general as the processing pipeline, and graph as an API graph, which applies to all of those elements here. So the Akka streams, not Akka streams, the stream processing world is quite big. You have a number of technologies here. This slide comes from my colleague's presentation about small introduction to big data. And you can see that actually Akka streams is not here even. So there's really a lot of technologies. So you may ask yourselves how Akka streams is different from the technologies that you can see here. Well, first of all, Akka streams is not distributed. Unlike, for example, Spark, where you can have a distributed setup with a number of nodes, Akka streams theoretically runs on a single node, although it may not entirely be true now, because, well, in Akka streams you separate the recipe for processing your data from the runtime. And there is a default runtime provided by Akka, which is based on an actor system. But it turns out that there are other implementations appearing of materializers, which are those runtimes. And one of them is a materializer based on Apache Gear Pump, which is distributed by nature. So it can mean that Akka streams could be run in a distributed manner. But this is like, I think it's kind of alpha. There's no production use so far. At least I haven't heard about it. So when defining an Akka stream pipeline, what you do is actually you define the small building blocks that you will be using to process your data. Those building blocks are reusable, so you can just define them once and use them in multiple graphs, for example. And it's very important that those building blocks are lazy. That means that nothing is happening before you actually run the entire graph. So the process of composing the graph is just writing a recipe for processing your data. But nothing actually happens when you write the building blocks. The only moment when something happens is when you actually run the graph using something that is called the materializer, so the, let's say, runtime environment. So now I'm going to quickly describe the example use case that we'll be dealing with, and then we'll jump to the live coding part, which is the main part of this talk. So our use case is importing a number of, like importing data from a number of files into Cassandra using some intermediate aggregations. So in our files, which will be gzipped, we are going to have a number of lines and each line consists of an ID and a value, and every 2 subsequent lines share the same ID. Then any of those lines can be valid or invalid. So we may have 2 valid lines, 2 invalid, or either a single valid line. An invalid line is indicated by an invalid line text that wouldn't be parsable to a double value. Now what we are going to do is we'll be streaming the files. Then we'll be taking each 2 subsequent lines, averaging the value by ID, and putting the average value in Cassandra. And for the invalid, if we encounter a case where both the values are invalid, we'll be using some dummy value for the average just to be able to store some dummy value for the ID. Okay, here, well, we'll be jumping to the live coding now. I want to thank one of my colleagues here who submitted a pull request to my code, adding waiver. So if you attended the waiver talk today in the morning, you will be able to see some of the usage in practice. And waiver is basically the former Java slang, and it's like kind of functional programming for Java. Okay, so here we have our CSV importer with some boilerplate. We have some configuration parameters here. I'll be explaining them when I use them, actually. And they are just read from a configuration file, and that's it. So the first thing that we are going to do will not have anything to do with Akka streams so far. We're just going to write a simple asynchronous method that takes a line, splits it by the semicolon, and then converts it to our domain model. So since we're going to be asynchronous, we'll be using the completable feature and related APIs from Java. So we're going to, our return type is going to be a completion stage of reading. Now reading is a part of our domain model. It's an interface that provides an ID, and it has 2 implementations. First of them is, it's a valid one, a valid reading that has an ID and also has a double value. The second one is an invalid reading. As I said, if we encounter 2 invalid lines, we still want to save the ID to the database with some dummy value. And this is why we're representing this case in our domain model as well. So we have a completion stage of reading. The method is going to be called parseLine. It's going to take a string with the line to parse. Okay, so since we want to be asynchronous, in every reactive system you don't want to block if you really don't need to, so we won't be blocking as well. So we'll return a completable future. We'll use a subline async method, and then we can just do our computations inside. Okay, so let's start with our line. We take our line, we split it by the semicolon, and this is going to be our fields variable. Now, first we want to extract the ID. So we'll say integer parse int, take the first value from the fields. This is going to be our ID. Now we are going to parse the value from the second field. This is our value. And, well, we could just try to say return a valid reading with the given ID. Sorry. It's a new valid reading with the ID and the value. But this is the happy path. So if the parsing succeeded, we could return a valid reading. But as you remember, we also need to handle the case where where the line was invalid. So we need to handle this as well. So normally what you would do in Java is to use a try-catch clause, but I'm going to use waiver here to see how we can use the try structure from waiver to do the error handling and returning and some other value in case of failure. So let's just delete those. And now I'll say return try, and this is going to be the waiver try of, Here I'm doing the actual computation that I attempted to do previously, so far nothing new. And now I'm using the map method, which basically says what we are going to do when the computation succeeds. So if the computation succeeds, we're going to get a value, the double value, and we can return a new valid reading with the ID and the value. Now, if something fails, we want to log in order to have some information about the failure. So we're just saying that we have an on-failure method that gives us the access to the exception, and we can just log the exception. And ultimately, we want to return another value when it fails. So we use the get or else method, which would either return the valid reading when it succeeded, or return something else when it didn't succeed. So in case it didn't succeed, we want to return a new invalid reading of the ID. And it doesn't compile yet. The problem is that when we use new valid reading within map, the compiler thinks that the return type of the entire structure is going to be a valid reading, and actually you're returning invalid reading in the last line. So what we need to do here is to cast the value that returned in map to reading, and then the compiler will know that what you're actually going to return is an instance of any subclass of reading. So this was the non-Akka streams part. We just parsed a line into our domain model. So far, so good. So next thing, and now we start dealing with Akka streams. Next thing that we need to do is having a stream of bytes coming from a file. We need to detect new line characters in the stream, and then emit another stream of bytes. But then the bytes emitted would be emitted line by line, so they would be separated by the new line character. So what we're going to define now is something called a flow. Flow, as you may remember from the slides, is one of the processing stages in the graph. Now, flow has three type parameters. The first two are pretty obvious. This is the input type, the output type. So we have a single input and a single output, and we have the types here. The third, called mat, is something called a materialized value. And materialized value is something that a graph can emit to the outside world. Because normally the in and out types are used for internal communication within the graph. So for communication between the subsequent stages of the graph, but those values are not visible from the outside world. I mean you cannot access them from outside the graph. They are internal to the graph structure. But there is the concept of materialized value, and it is something that can be emitted outside and can be accessed from outside the graph. Actually, in our case, we won't be using the materialized values because we'll be writing building blocks that just construct the graph, and we'll only be dealing with the types that are inside the graph. So here the types are, this is something called byte string, which is basically like, it's a stream of bytes. It's a type internal to Akka. So the input type will be like a sequence of bytes. The output will also be a sequence of bytes, but it would be delimited by new lines. And here for the materialized value, we're going to use a special type called not used. Now, why not used if you have void in Java, for example? Well, the problem is that Akka streams and the Akka team aims for the library to be like easy to use both from Scala and from Java. And now in Java you have voids, in Scala you have a unit type. And those types, well, they symbolize the same thing, but they are not fully interoperable. So you wouldn't be able to fully use unit from Java or to use void from Scala. And that's why a special type called not used was created, and it's basically a combination of Java's void and Scala's unit, nothing more. So now we have, it needs a name. So it's a line delimiter. Now we have a helper class for it called framing and the delimiter method. And basically, well, first of all, we need to provide the separator. So we say byte string from string new line character. Then we need to provide the maximum length of the line we'll be parsing. Well, in our case, the lines are pretty short, so 128 is a sensible default. And the last parameter, it's a flag called allow truncation, and it basically says whether we allow for the delimiter not to be present at the end of output. So basically, if we want to handle a case where there is no new line character at the end of file, we need to set this flag to true. So that's like short set. So we'll just say framing truncation allow, and it says it means that when there is no new line character at the end of file, it wouldn't fail, but it would still return the last line. If we set it to false, so like to an enum value, then it would fail if no new line character was present. So that's all for the line delimiter. Next thing, the next flow we would be implementing would be actually parsing the file. So once again, we'll be defining a flow. So we'll be using the flow class heavily here because it's the like basic starting point to defining your own building blocks. Now the input type of a flow is a file that like it's a Java.io file. The output type is a reading. It may be either a valid one or invalid one because, as you remember, when we were parsing the files, we could emit either a valid or an invalid reading. And the materialized value is not going to be used because, well, we don't emit anything outside. So now, to create a new flow, we just say flow of. Then we provide the class of the type of the input parameters. So here it's going to be file.class. Now I'm going to use a flatmap concat method. I'm going to write a little bit of code and then I'll explain what it's doing. So don't be scared by the perhaps not meaningful name. So we're going to have a file, the access to every file here. And for every file, well, first of all, we need to like have some input stream from which we can read the contents of the file. So we can create a new gzip input stream from a new file input stream from the file. And this is going to be our input stream. And now we're going to use a helper class from Akka streams called stream converters. We can pass an input stream to it, or actually a function that creates an input stream. And what this method does, if you look at the type signature, it returns a source. So source in terms of Akka streams is the producer of data. And now it's time to explain why the flatmap concat method here. So you can notice that here for every incoming file, we are going to produce a source. So having a number of files, we're going to have a number of sources. And actually what we want is a single source that emits readings. So in order to create multiple sources, in order to create a single source from multiple sources, we use the flatmap concat method, which basically it takes a piece of code that returns a source, and then when like multiple calls of this method return multiple sources, it flattens the sources and concats the elements that come out of these sources. So basically here we'll have a source for every file, and with flatmap concat we will turn these multiple sources into a single source that is going to emit readings. So now having the stream of bytes from the stream converters from input stream, we need to use the via method, which basically is used to combine different flows together. So now we can specify another building block that we want to use here, and the building block we want to use here is the line delimiter. Now, since our CSV files can or cannot have a header line, we want to be able to skip an arbitrary number of lines from the very beginning. So we're going to use the drop method, which may look familiar if you use the collection API. So one of the configuration parameters we had was lines to skip. So we can skip a number of lines. And now, since what we have here is a byte string, and we want normal strings, because our parseLine method that we wrote at the very beginning accepts normal strings, not UTF string, not the byte strings. So we need to convert our byte strings into strings. So we have the byte string UTF-8 string method. And this is the moment where IntelliJ gets crazy. I don't know why, but it's like the auto-completion is now broken. It needs some time to think about it. I don't know why is that. It's perhaps because the byte string has a lot of methods and the method references don't work. I don't know. If any of you knows, I'll be happy to hear how to fix it. Okay, so it looks like IntelliJ caught up here. So now the last thing we want to do with our strings is to actually convert them into our domain model, so to call the parseLine method. And we want to do it in an asynchronous fashion. but we want to keep the order of the results. Because in the further processing stages, we'll be grouping the readings into groups of 2 in order to be able to average them. So here, when running the asynchronous computations, it's important to pass the elements downstream, so to the subsequent steps, in the same order in which the lines arrived. So that's why we're using the map async method here. It has 2 parameters. First is the parallelism level, so basically a number of parallel computations that are going to happen. And we have a configuration parameter for it. It's called non-IO parallelism for all non-IO operations. I mean memory computations like this. And here we'll just reference the parse line method that we defined earlier. So this is to recap this step. This is a part that is used to parse, to define a recipe for parsing a single file. And basically, it accepts files, and then the method we created produces a source from each file. And then we are using flatmap concat to flatten those sources and concatenate them, so to create a single source out of multiple ones. So that's for this one. The next thing we are going to do is to compute average. So computing average means that we want to take every 2 lines, every 2 readings actually, then extract only the valid ones. And if any of them is valid, we want to calculate the average. If not, we are going to return a dummy value of -1 in our case. So once again, we're starting with a flow. This time, the input type of the flow is going to be a reading. And the output type will be a valid reading. Since we only want to emit a valid reading, if both of the lines were invalid, we'll also return a valid reading with a value of -1 for a given ID. And the materialized value is once again not used. It's going to be called compute average. Okay, so once again, we say return flow of, now it's reading.class. Now the first thing we do is group the readings in groups of 2. So we have a grouped method that takes an integer, and this would emit collections of size 2 in our case. And now we also want to process to calculate the average asynchronously, but this time we no more care about the order, because if we already have the lines in the proper order, the readings in the proper order, after we aggregate them into a single reading, a single valid reading, we no more care about the order. So we have an unordered version of the map async method we used previously. This version is certainly faster. It can be faster because it basically emits the elements downstream as soon as any computation is complete. So it doesn't need to wait for every computation to complete before passing the elements downstream. It rather just emits anything when it is ready. So once again, we're using the non-IO parallelism here. And what we are going to get here is a collection of readings. So this is the result of applying the grouped method. Now from the readings, sorry, I was expecting a larger resolution here, so I hope it's still readable. So we're going to use completable future once again, supply async. And then what we do here, I'm going to use waiver here once again for easier list processing. So I'll be using a list class, but not the Java util one, rather the one from waiver. This lets me say lists of all readings. And then what I want to do is filter only the valid readings and have a list that is a list of valid reading and not a list of reading. So I'll say filter, take the isInstance method from the reading class, and then I just need to change the type because this would still be a list of reading and I want a list of valid reading. So I'll say valid reading class cast. And now I have a list of valid readings, so that's actually what I wanted to have. So now I take the valid readings, map them to their value, and then the waiver list gives me an average method. So I don't need to use any collector. I just have an average method, which has a pretty nice signature in our case because you can see that it returns an option. And actually, it returns an option when if the list is empty. So this is perfect for our case because if the list is empty, it means that there were no valid readings. So this would be like an easy way to handle the empty list case to return a default value. So we'll use the average, then use get or else. And so if the list was empty, we're going to return a dummy value of -1, which is the dummy average here. This is going to be called average. And we're going to return a valid reading. Now we need an ID. But, well, we had a list of 2 readings. It doesn't matter whether they were valid or invalid. They still would have an ID anyway. So we can just take the first reading, take the ID, and then return the average here. So this is the average computation part. Once again, we basically group the readings in groups of 2, and then asynchronously compute the average out of them. And we handle the case where there is no valid reading at all. Then we return the dummy value of -1. So the next small step will be to combine the file processing, the 2 stages that we defined so far, into a single flow, so that we can reuse it later. So we'll define a flow whose input is a file, whose output is a valid reading, and the materialized value is not used, and it will be called process single file. And we're going to, well, once again, we're going to say flow of file.class, and then we're going to use the via method twice. So first of all, we're going to say via parse file, which is the first flow we defined, that converts a file into a source of readings. And then we're going to say via compute average. Now the via combinator is type safe, which means that, that the compiler checks that the types are consistent between the subsequent stages. So for example, if we reverse the order of the stages, it wouldn't compile because, well, for example, the parse file emits a reading and the compute average accepts a reading, so the types need to match, and this is verified at the compile time. So this is for processing the file. The last thing we need to do is to store the readings into our database, into Cassandra in this case. And storing is going to be the ultimate step of our processing pipeline. So this would be a consumer in the general architecture, and a sink in the Akka streams naming conventions. So what we want to use here is a sink. And you can see that sink now has just 2 type parameters, because it only has an input and the materialized value. It doesn't have an output because it's the ultimate stage in the processing pipeline. So the input type is going to be the valid reading. And in this case, we'll be interested in the materialized value, because we want to know when the stream processing is complete. So we want to have a kind of a future value that we'll be able to wait for at some point. So we'll use as the materialized value, we're going to use the completion stage of done. Sorry. Now done is a bit similar to not used. It's like another wrapper that combines void and unit, so that it combines the Java word with the Scala word. So, well, the naming is different, but the purpose is pretty much the same. It would be called store readings. And now we're going, well, we'll once again start with a flow. Now what we want to do is asynchronously and in parallel store the readings to Cassandra. So we're going to use the map async unordered, this time with different parallelism level, because this is an I/O operation. We have a configuration parameter for this. It's called concurrent writes, and it's the number of writes that can be made to the database in parallel. And we have some reading repository that has a safe method. And the only thing you need to know about it is that it takes a valid reading and returns a completion stage of some result set. This is the result set from the Cassandra driver, but it's really not important here. So we'll be just calling this method asynchronously. So now we have a flow, and we want to convert it into a sink. So we need to, what we're going to do is to connect this flow to a predefined sink from Akka streams, which is called sink ignore. And sink ignore basically ignores all the elements that come in, but it waits for the stream to complete. And this is actually what we want to do. We don't care about the values of the elements. We just want to know that all the elements were processed and the stream is complete. So we're going to use a toMat method. I'll explain why toMat and the naming in a second. Just let me finish writing it. So we're going to use sync ignore. And now, when you imagine the picture of what we are doing, is we have a flow and we have a sync here, and we're connecting those two. And both of those elements, like the flow and the sync, they can emit a materialized value because both of them have a materialized value in their signature. And if you're connecting them together, the flow is to the left and the sync is to the right. And what we are interested in is the value from the sync, so the right value. And when connecting two things together, we need to specify which of those two materialized values we want to take. So if we wanted to take the value from the flow, we would take the left value. If we wanted to take the value from the sync, it would be the right value, which is our case. So for this, we have an additional parameter that is called keep, and it has a write method, which basically says that we're going to only take the right value and disregard the value from the flow. Now, this is why we are using the toMat method. We also have a to method, which does the same, which lets us connect a flow to a sync. But the to method, by default, takes the left value. So this is not our case. We want to take the right one. That's why we are using the toMat version and explicitly specifying that we want to keep the value from the right, so from the sync. So now it's time, well, so far we have defined all the building blocks, so now it's time to tie them, put all of them together and see if we can run it. So now we're going to create a normal method, not a flow, not anything, just a method that whose return type is completion stage of done. It's going to be called import from files. And well, the first thing we need to do is to get a list of the files that we want to process. So I'm using a list of method here. Please remember that it's not Java 9, it's waiver here. We have a configuration parameter from the import directory. We say list files. And those are our files. We'll do some logging to see what's happening. We'll log the start time to do some benchmarking, or at least to know how long did it take. And now, well, we need to return something. And now when composing the entire pipeline together, we need to start with a source, then we need to add the processing stages, and then we need to attach a sync. And this is the entire pipeline. So we haven't used a source so far, but here is the time to use it. And we have a factory method for a source, which constructs a source from an iterable, which is our case because we have an iterable of files. So we just type files here. Now the source has also a via method, which lets us specify a flow through which we want to run the data. This is, in our case, the process single file. And then, well, theoretically, we would need to first attach a sync and then run the entire pipeline. But since this is something that you do very often, because, well, if you attach a sync, you also want to probably run it with the sync, there is a method that combines those two. It's called run with, and so it attaches a given sync and executes the entire pipeline. So we'll say run with, and here we're going to use our sync used for storing readings. So store readings. We're going to do some logging afterwards. It's basically checking if it completed with a success or failure and logging the processing time. And we can see that it still doesn't compile. Okay, you may not be able to see it, but the error message here is that we are missing one parameter from the run with, because we have the sync, but the compiler complains that we also need a materializer. So this is to remind that everything we did so far was lazy. So we didn't run anything. We didn't do any processing at all. And only in the run with method is the time when we'll actually be running something. So we need the materializer, which is the runtime for the entire processing graph. And as I said, in Akka streams, we have a default implementation based on an actor system. So it's called an actor materializer. And we have an actor system as a dependency of our class, so we're going to use it here as well. Okay, this may look like it's enough, But now you can notice that we are processing like the files one by one. So we're parsing a file, emitting the readings downstream, then parsing another file and emitting the readings downstream. And what we would like to do instead is to load balance the processing of the files. So we want to define a number of workers that would process the files in parallel. And then, so we would have a point where the files will be load balanced to a number of workers. And then the results of those workers will be merged into a single node and then emitted downstream for the average computation. So now we'll try to implement our, well, a bit more generic load balancer. So we're going to create a new class. It will be called util balancer. Okay. And it's going to have a single static method with two generic parameters, in and out, because, well, we wanted to, this example is to show how to use the GraphDSL API for building your own well, parts of the pipeline. So we have two type parameters, and we'll be returning a graph. Now, graph in Akka streams has two type parameters. First is a shape, and the shape basically says whether it's how many inputs and how many outputs the graph has. So we have, for example, a source shape which just has a single output. We have a sink shape that has a single input, and we have, for example, a flow shape that has a single input and a single output. And that's what we are going to use here. So we are going to use a flow shape with the in and out parameters, and not used for the materialized value. So the method is going to be called create, and we need two parameters. First is the number of workers for the balancer, and the second one is going to be the actual worker. So in our case, it will be a flow. So this is a flow with types in and out and the materialized value of not used. And we're going to call it a worker, and it's the Akka streams worker. So now we'll be using the GraphDSL with a factory method called create. And what it basically does, it gives us a builder instance, which we'll be using to manipulate the graph. So the first thing we need to do with the builder is to add a balance stage. So there are built-in stages that do the load balancing, which so splits the processing, and there is a built-in stage called merge, which does the merging into a single node. So we'll use the built-in balance stage with the type of in, and we need to specify the number of inputs, and here it's going to be the number of workers. And the builder the builder basically manipulates the structure of the graph. So we are using it to add this to our graph structure. So this is going to be called balance. In the same way, well, in a similar way, we're going to add a built-in merge stage with the type of out, and also with the number of workers, and it's going to be called merge. And now what we'll be returning is a flow shape, because we need to, in the builder, we need to return a shape of. And now we need to take the balance stage and take its input, because this is going to be the input of our flow. And then we need to take the merge stage and take its output, because this is going to be the output of our flow. And theoretically, it could be enough, but what we still need to do is to connect everything together. So basically for every input and output, we need to connect everything. That's what we are going to use an iteration for. So we're going to say in-stream range from 0 to number of workers for each index I. The first thing we need to do is to add the worker to our graph, and we need to add it multiple times, because, well, the worker is there is a single definition of a worker, but we need to create a separate stage in the graph for every instance of worker that we need, for every appearance of worker that we need to use. So this is going to be called the worker stage. And now we need to use the builder to connect everything together. So we'll say from we take the balance, we take the output number I. Then we connect it to the worker stage. And then we'll say to inlet, and will take one of the inputs of the merge stage. Now this is important, and this is going to be verified at runtime because Akka streams won't let you leave any dangling inputs or outputs, so you need to connect everything. And this is the Java API, which is, well, not that pretty here. And actually, if we did it in Scala, we could just use those pretty arrows. So we would just say balance, arrow, worker, arrow, merge, and this would do the entire iteration and do the builder add and combine everything. So this is like one of the drawbacks of the Java API. In Scala, it is, well, prettier. And the last thing we need to do is to create an instance of our balancer. Oh, I'm sorry. So we say balancer create. We have a configuration parameter for concurrent files. Our stage is process single file. We're going to call it a balancer. And here we need to substitute the process single file for the balancer. OK, so that's it. And now we have a Docker. We have Cassandra running in a Docker container with a readings table, which is now empty. So now I'm going to run. Oh, and it won't run because we're missing a main method. But that's not a problem. The main method, what it basically does is to load the configuration, create the actor system, create the repository, and then like tie everything together. So now it should run. Let's see. We're going to have some error messages here from the invalid lines, so that's why we implemented the logging for the invalid lines. OK, and we have finished the import, so let's see if anything is there in the database. So something is there. Let's count the values. And we have, yeah, it matches the number of files. It should be 50,000, but we had some random invalid lines in the files, so that's why it's a bit less than 50,000. But it's almost there. OK, so that was for the live coding part. So now certainly there is more. So I have shown you like the built-in flows, the built-in things that you can use. I showed you the graph DSL for creating like your own building blocks with a like a little bit low-level DSL. But you also have there is more. So you can build even more complicated building blocks that are stateful, for example, because here all the blocks were stateless. But it's possible there is an API for creating stateful blocks as well. Actually, I've written a blog post about this, so there will be a link at the end, so you can read it and like try to build it yourself. So thank you for your attention. This QR code has the link that is below, so this is the same. There is a landing page with links to GitHub, so the entire source code is online. There is a link to the blog post, and there are contact informations. If you have any questions, we have still 2 minutes left. If not, if you don't want to ask now, you can catch me tonight or tomorrow. Thank you for your attention.